So a zero, or a root of a polynomial over a field, is an alpha that evaluates f at 0. So if you replace every x in your polynomial with alpha, you get 0. Now notice I'm intentionally ambiguous about where alpha is. It doesn't necessarily have to be in f. So let's do an example. The square root of 2 is a root of the polynomial x squared minus 2, and that's a polynomial with rational coefficients. So I am in the field of rational numbers with my polynomial, but my root is not a rational number. That's okay. So here's a theorem. The theorem is alpha in my field, so I'm going to say alpha in my field is a root of f, which is a polynomial with coefficients in my field, if and only if x minus alpha divides my polynomial. Now, what does divides mean? It means when you do division with this as my f and this is my g, I get remainder 0. So I'm defining divides in polynomials to be remainder 0. So let's prove this. It's not too difficult of a proof. It's an if and only if. Let's first assume that alpha is a root. So using division, I know that my f of x can be written as some q of x times x minus alpha plus some remainder term r of x. With the degree of the remainder term has to be less than 1. So the degree of the remainder term has to be 0, meaning this remainder term is just a single constant in my field. Now, if you evaluate both sides at alpha, what you get is 0. I'm assuming that alpha is a root, so if evaluating f at alpha gives you 0, if I evaluate this term at alpha, I get 0 times q, so I get 0. And if I evaluate r at alpha, I get just that constant, a0. So I guess a0 equals 0, and that's how I've defined divides. The remainder is 0. So that's one direction. And then the other direction, I'm going to assume that this term divides my function f. So by hypothesis, what that means is there's no remainder. So when I do division, I get q of x times x minus alpha. And now you evaluate at alpha, you replace every x with an alpha, and I see that f of alpha has to be 0. So that's the theorem. It's a pretty simple theorem, but it's a pretty nice one nonetheless. As a corollary of this theorem, a polynomial f in my polynomial ring over a field f of degree n has at most n distinct roots in my field f. Okay, so let's prove this. I'm going to use induction on the degree of f. So by induction on the degree of f, what's the base case? I guess the base case would be f is just a constant function, degree 0, and then it has at most, if f is a constant function of degree 0. It's just a single non-zero constant. Remember, this would be the leading term of my polynomial. The leading term cannot be 0. So that would mean I have 0 distinct roots in my field. So I think the base case is okay. So let's suppose alpha in my field is a root. If that's the case, then that means I can use the previous theorem and write my function f as x minus alpha times some other q of x. The degree of q of x has got to be smaller than the degree of f of x. So I could use induction on q of x. So applying the induction hypothesis, q of x has at most n minus 1 distinct roots. The roots of q and f match except for alpha, so that means we're done. F has the roots that q of x has and possibly one new one in alpha. So I think we're done. All right, great.